All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to continue with the LeRoBotics. What was it called? LeRobot. We're going to continue studying about LeRobot through the robotics course on Hugging Face. Now, before I started today's stream, um, I was kind of torn between whether I should do um, whether I should just do a Rust study stream because there's still some of the Rust basics that I haven't, gotten to. Let me show you where. Um, I think I have the conversation open here. It should be in this, I believe. No, in this. In I think it's this. Yeah, I think it's this. Hold on. Is this teaching me about hash something? Hash map? Well, this is about strings. Hash maps, yes. So I finished hash maps. I finished the topic after that as well, which I believe was generics probably. Let me just Yeah, it was generic data types, functions, and methods. That was an interesting topic to get into. Um, and then I am almost done with the current topic, which is traits. There was also generics continued. They were teaching various things. It was actually a really interesting topic to get into because I believe I did also look into how generics are handled during compilation, and like when you have different concrete types being used for a specific generic, then how is the compiler handling all of that? So it was really interesting to get into that. And then we went into traits, which is here. And this is another super interesting topic, especially so traits by themselves, like that's an interesting topic of its own, right? But then when you combine it with generics, then it becomes an incredibly powerful thing that lets you implement a whole bunch of very advanced and sophisticated functionality. So I was in this chapter. I never finished this chapter, and that's kind of why I want to continue. This conversation has been going on for a while. I don't want to scroll up too much because I don't want the thing to like load all of that if all of that happens to be already loaded. But we which chapter does it mention the chapter number? It says chapter 9 traits. Chapter 10, I believe. I don't remember what the syllabus was. Did I even like export the syllabus anywhere? Where am I? Temp Rust Learning, Gemini Rust Learning. Okay. Uh, Here's what we can do. Okay. We're gonna go in here and look for EFGH G Gemini Rust Learning. No. Um, yeah. Okay. Where is Gemini Rust Learning then? Um, is there a way for me to um, run a command here? No, hold on. Rust proj doesn't have it. No, no. Um, Gemini. Okay, okay. Yeah, no, it's none of these. I'm gonna have to look where exactly I stored the syllabus, but it's somewhere here. It's definitely somewhere here. Or it might be like back here, but I'm not sure. Either way, yeah, okay, anyways. I'll have to look at the syllabus. There's probably 3 or 4 more chapters, and like each of them, I think after this we get into heap related stuff. Um, yeah, I think after this we get into heap related stuff. So, anyways, I was wondering if I should, continue with the robotics course reading, which I was going to continue with it anyways. I was just wondering for today if I should do that or not, because there are a bunch of like projects that are like I'm getting ideas for them, which I kind of want to get properly comfortable with all of the Rust basics. And yes, that includes the bare bones multi-threading stuff as well. I kind of want to get comfortable with all of the Rust basics before I start going into more advanced stuff. Like, for example, just for my curiosity, I kind of wanted to try and load a GLTF scene, a 3D model scene, basically, or well, an entire scene containing 3D models that's been exported as a GLTF file. I kind of wanted to write a Rust program that can render that entire scene, and then maybe I could like walk around or fly around in that scene. I also was tempted to write a sort of VRM viewer. VRM is a file format that I believe it's based on GLTF, but it has a couple more extra features that are specifically for avatar model related purposes. And where was I going with this? Yeah, I kind of wanted to try and write a simple VRM model viewer. I guess we can call it that. I wanted to write a very simple VRM model viewer using Rust and Nano. I would probably benefit from using Bevy instead, but I kind of want to stick with Nano for now because my that's kind of what my system resources will currently allow for. Because when I try to open up a Bevy project, the Rust analyzer takes up a good, like, I don't know, 5 to 6 GB, right? And that's just having a bare bones Bevy project open, right? So 5 to 6 GB is gone in that. And then when I run the build process, that's going to consume a couple of GB as well. So then memory starts to fill up really quickly and it can cause issues. I have much lesser problems when using Nano, and I kind of want to stick with Nano. One of the biggest reasons is because Nano is for creative coding. Bevy is a game engine, right? These two frameworks have different purposes. They're not meant for the same thing. You could use them for different purposes. Like uh, you could use Bevy for something that you're meant to use Nano for, and you could use Nano for something that you're meant to use Bevy for. That's perfectly fine. It's just that each of these frameworks, they have different ways of doing things, which in certain cases they are beneficial. Like creative coding, there's a very specific style of coding, which doesn't constrain you a lot, right? And that's incredibly important for creative coding because you're not necessarily creating a game. You need creative freedom to be able to just draw whatever you want, right? And then you have something like Bevy where you are forced to follow a fixed structure because that's the way that you are able to create the experience they're trying to create in a more optimized and a more efficient way, right? You're kind of locked in with a certain style, a certain pattern. You're not very much locked in with something like Nano. There are, of course, pros and cons. Like the locked in thing with Bevy, it does allow you to benefit from various performance optimizations if need be, right? The same thing if you try to do it with Nano, then you're going to have to, I mean, you're still going to have, you would be able to use certain types of performance optimizations, but when you go for that creative coding style, then you kind of do trade off some of the performance optimization and efficiency, and or rather, you trade off the ease of implementing performance optimizations and various types of efficiency um, things. Anyways, point being, I want to use Nano. Forget about my reasoning for why I want to use Nano. I want to use Nano because, like, a lot of the other projects that I plan on working on, they're all like, I'm thinking of them in terms of Nano. I'm not thinking of them in terms of Bevy. And anything extra that needs to be implemented, I'm going to implement it manually. Um, I'm not expecting them to be very tightly knit, very tightly packed, or very tightly um, supported. What's the word I'm using? What's the word I'm aiming for here? I'm not expecting them to be very tightly integrated. That's the word. Any extra like packages that I might be planning on using, I'm not expecting them to be very tightly integrated with Nano. So Rapier, for example, the physics library, I'm not expecting it to be tightly integrated, and that will have its pros and cons. Um, However, it doesn't make it completely impossible for you to you know, use the Rapier library with something like Nano. So, anyways, I wanna write a sort of VRM model viewer in Nano for one, getting better at Rust. Two, getting better at Nano, getting more comfortable with the Nano framework, and three, just because I want to build something like that, because I've been curious about that. Now, one challenge that I might face is that Nano is mainly meant for drawing 2D stuff. The API that it provides you, at least from what I understand, it's more geared towards 2D stuff. Um, I could be completely wrong about this, okay? Completely wrong about this. Maybe there's like a whole bunch of 3D stuff. I mean, there is 3D support in the API. I just don't know if the API is designed in a way that you are meant to be drawing in 3D space, or if you're meant to be drawing in 2D space, and you can display 3D in 2D space. But like, there's a difference there, you know. Like, if you're meant to be drawing in a 2D space, the API is going to be designed in that way, and then anything 3D that you are trying to do, you can do it, but like, there's going to be certain limitations because there's different ways that you are displaying this 3D stuff. So I need to look into what that's like. Anyways, enough about Rust. Let's um, let's read up on LeRobot. How much time have I lost just yapping about this? 13 minutes. Okay, we are 13 minutes into the stream. Um, I'm gonna continue with the Rust uh with the Rust basics thing. I do want to finish the. You know what? I'm just gonna scroll up. I'm gonna scroll up and take a look at. Okay, you know what? I guess the thing was already loaded, and I was just unnecessarily trying to avoid loading it, because judging by how fast it scrolled up, I think it was already loaded. Right. So, oh, lifetimes. After traits is lifetimes. So lifetimes is one that's remaining. Um, and after that we have closures and iterators. I completely forgot about that as well. Fortunately, I have covered both of these. I just haven't covered them as deeply as I would like to. So it should be interesting to get into both of these topics. Um, After I'm done with traits, for the time being, I'm currently trying to refresh my knowledge on hash maps, and I need to do a bit of experimentation when it comes to vectors and slices, because I kind of feel like I haven't fully understood everything surrounding slices. And in order to, you know, benefit from it and use it to the best of its abilities, I kind of want to understand slices much better. I don't know if slices get covered here at all. I don't want to like take the tutorial in like a different direction. So I could just Google slices. I think slices did get mentioned at some point. Um, it should be mentioned under collections usually. Something like vectors. You can pull out a slice of a vector, so you don't have to do like a whole for loop and populating an array and stuff like that. It's like a very simple line that you can actually hold on. Let's open up. Um, okay, we can close this for now. That's going to take some time to close. Let's open up a new window. Let's cd into Scratch stuff, and I believe Rust proj01. Open this up. Okay, no, don't open that. That's let's close that and open that. Okay, so here we have, oh yeah, this is exactly what I was trying to do. I was trying to see if this is possible because I have been playing around with like slices and stuff. Um, yeah, this is about as simple as it is. In order to pull a slice of this array, I need to also look up the difference between array and vectors in um, in Rust, because there is definitely a difference. There's definitely a difference between arrays and vectors. Actually, okay, this is an array. This is an array, right? We can do, okay, let's say E equals vec. So this creates a vector. 3, 4, 5, 6. Okay, now let's see if we are able to pull a slice out of this. Um, let's see if that gives an error. Give it a second. Okay, it's not giving an error. What we can do is print line. I don't think this is necessary. Oh, this is necessary, but I don't think this would have been necessary. Right, and then we print out F. It is necessary. Never mind. So let's do cargo run. We'll get to the robotics course like real soon. Just give me a second here. Yeah, okay. Slicing works for vectors as well. So I need to do a bit of research on. Actually, let me open up a Gemini conversation and just pop in the question, just so I can remember later on that hey, I was having this conversation. So I can take a look at the conversation off stream and continue reading up on this. Hey, so I'm learning Rust. I'm I have covered some of the basics. I've learned about stuff like vectors. I'm confused. Actually, okay, I think one of the differences between vectors and arrays is that one of them can be resized and the other is fixed sized. I don't remember which one has like a strict data type um, limitation, as in you can't have multiple data types. So let me try putting a float in here. Mismatch types, expected integer, found float. All right, let's try doing this with the array instead. Now there's an error here as well. So I'm confused because I know for sure, was it tuples? It might have been tuples. Okay, let's try G equals 1, 2.0, and are characters a thing in Rust? I think they are. Yeah, so in tuples we can do that. That's fine. Um, Yeah, yeah. I can't remember. Hold on. Let me just pop that question in. I'm I'm I would like to understand. I don't think I need to mention that I've covered vectors. I would like to understand vectors, arrays, and slices better. It's great that you're diving into Rust. Understanding the difference between these three types is a light bulb moment for most Rust learners. They all store sequences of data, but they handle memory. Oh, is vector on the heap? So arrays are fixed and fast. Okay, fixed length and fast to access. Vectors are dynamic and they are stored on the heap. Arrays are not stored on the heap. Arrays, I believe, are stored on the stack. Yes, an array is stored on the stack. And then we have slices. The view into data. A slice is a reference to a contiguous sequence of elements in a collection. It doesn't own the data, it just points to it. This is why slices are almost always used as references. The syntax is so and so. All right, you know what? We're not gonna get too sucked into this because we have to do the robotics thing. Real quick, I wanted to wait. Let me close this so I don't keep getting distracted. Let's get back to this, and now let me read this. So I think I should have read the section where it mentions how to use the course material. I don't know if they mentioned this. Learning assessment, hands-on code examples, interactive quizzes, progressive difficulty, real-world applications. What's the recommended pace? Take your time, try the code examples, take the quizzes, try the code examples. Okay, I think they might have been pointing towards wait, okay, how to get the most out of this course. To get the most out of this, practice with the code examples, take the quizzes seriously, and explore beyond the course. Try LeRobot examples, experiment with. So all of these examples that they're talking about, they're all mentioned in. Um, do they have a link to it here? No, it might be here. Give me a second. Um, LeRobot repo. Okay, course introduction to robot learning. We are going to be going to classical. Actually, there was a thing here that I hadn't looked into. Right, code example, batching streaming dataset. Did I finish reading up on LeRobot dataset? Because actually, I didn't. There was a words. There was a bunch of stuff in the LeRobot dataset section that I didn't read, and I feel like just reading it is not going to be enough. I definitely need to practice it with the code example. And fortunately, I have my entire environment set up here, so I think I can get started with the code example thing. I was planning on like reading this classical robotics thing because this goes into like a bunch of very interesting information. It explains um, at least from my brief glance of it, it explains what the problem is and how you solve it, and also the math side of things. But at the same time, I don't think we'll need to get too deep into the math side of things. Um, they're explaining it, but I'm pretty sure we will be able to use like already written functions, already made algorithms. We won't have to implement all of that math by ourselves. Which is kind of interesting because, dude, I'm gonna I'm gonna be honest about this. Okay, when I first um, when I first started doing research on ML and reinforcement learning, I didn't really know too much about deep learning at the time. But when I first started doing research on ML and reinforcement learning, something that kind of kind of made me turn away from it was how heavily whatever I was learning, the path that I had taken, how heavily each of those paths were focusing on the math behind this. And I'm not saying that focusing on the math is a bad thing. It's a great thing. It's amazing because that teaches you the basics and that teaches you how to implement these various libraries that we are using these days. But I kind of feel like that also made it daunting because I didn't really understand the math. And because of that, I didn't fully understand. Because of that, I wasn't able to like keep my attention on it for very long. Because it was like, okay, when they're teaching you this stuff, and I didn't understand this at that time, but when they're teaching you this stuff, they're teaching you they're teaching you how to solve this problem mathematically, but you then have to think of a way to apply this solution programmatically, not mathematically. Like you have to implement this, but programmatically. And at the time, I didn't know that, yes, there are libraries that you can use for doing this stuff. So when I first started doing research on either ML or RL, I would look at like a bunch of lectures and stuff, and a lot of them were focusing very heavily on the base math, and that kind of like it made me turn away from it. Whereas if I would have started learning this stuff using something like the Kaggle platform, where they focus on stuff like scikit-learn, rather than going too deep into the math, then I would have picked it up much quicker. Um, Stuff like PyTorch, for example, which is a deep learning framework. I first started learning about deep learning through one of the MIT lectures. You guys should definitely check those out. Incredibly helpful. I think every year they do a new one because I think I've been seeing new ones like in 2023, 24, and 25 as well. Um, I don't remember exactly, but like there were multiple versions each time. Like they do this course every year. I don't know if they're planning on doing it this year. I hope they're planning on doing it this year, and I'm sure it's going to be refined a bit more to keep up with the current stuff that's going on, the current tech. But what they teach you, they start with the basics. They teach you first. They go into like some of the history and what problems they're trying to solve or what problems deep learning is supposed to solve, and then they slowly take you into each of the different neural network architectures. They start with a feed forward neural network. Before feed forward neural network, they'll teach you like even more basic than that. They'll teach you about like a simple perceptron. It'll be like one neuron and one input, and then you do some kind of operation over there, some kind of calculation there, and you get an output. And how do you make this work? Like, what is going on here? They teach you like from the very basics. They teach you like a building block kind of thing, right? And then they teach you how these building blocks can build a bigger network, which eventually leads you to a feed forward neural network. Then they take you towards recurrent neural networks. Then they take you towards convolutional neural networks, and then they go into like a couple other architectures as well. I don't remember if they do actually go into the transformer architecture. I think they do. I just never got to those lectures because I was still hung up on feed forward neural network and convolutional neural network and recurrent neural network. But the thing is, I was going through those lectures. They're on YouTube. They're available for free if anyone is interested. There's actually a website on which this entire course gets, like, all the information gets hosted. There's the lecture, and for each lecture, there's usually a lab segment as well, or labs segment, whatever you call it. Basically, they'll give you like a code lab. It'll be like a notebook kind of thing where you can. Um, I haven't opened it, so I can't say for sure if it's like a quiz kind of thing, or if they're just giving you examples and then you have to implement it yourself. But basically, they'll teach you how to implement this stuff practically. Let's just say it in that way. It is incredibly helpful. Um, I didn't go all the way with it. I just watched the first three or four lectures, and then once I got into PyTorch, I kind of just took my research in a different direction. And I'm still planning on learning about these architectures, as I've been saying in multiple streams now. I'm still planning on learning about these various architectures. It's just I'm going to learn in a different, in a much different way. Okay, that being said, let's. Um, what was I gonna do? So there was the notebook that I need to open. So we're gonna open up this tutorial space, this Hugging Face space thing. This is gonna take a little bit to load, so let's let that do its own thing. Okay, LeRobot, an open source library, LeRobot dataset. We did read LeRobot dataset yesterday. This is all about loading data sets specifically. I think, in fact, LeRobot dataset, I think that's also the name of the format. Um, Let me just confirm that. Yeah, it's a standardized dataset format designed to address so and so, so and so, so and so. So yeah, we were reading up on this format, and in the next thing, they show us how to use it practically. So that's what we're gonna do. I hope the data set that I have to download is not too big, and I'm able to download it on stream. Okay, code example, data sets in practice. Real quick before we do this, we are just gonna read. Wait, this is available in PDF form as well. I need to, by the way, okay, this entire thing, I need to look into how. Wait, I want to load this on a different machine. Robot learning a tutorial. Yeah. Okay. I'm gonna look that up. Hugging face space robot learning. Robot learning a tutorial. I'm gonna open up the space separately because I'm curious about this UI that they've set up. It's kind of interesting because this table of contents thing is especially interesting to me. That I'm able to click on any of these and it just jumps to, that section of the page. I'm just gonna zoom out here. Oh, okay. You know what? I can probably show it here. The table of contents. Let me just zoom out a bit more. Yeah, this is the table of contents. This is what you guys were seeing. And here it's only showing like the main topics, but then there's subtopics as well. So, okay, let's click on introduction. And then, okay, that's when subtopics open up. Right. So this is the entire thing. So I need to look into how they, because I remember Streamlit has a thing that lets you implement something like this, but those are like different pages. They're not the same page. Here it's helping you jump. Maybe, okay, I could look at the code um, for this space, right? I can analyze the code for this space and see how, um, just a second. Yeah, I can analyze the code for this space and see how the table of contents thing is being implemented. All right, so we have read through this. Actually, have we? I'm not entirely sure because I think there's different information on this page versus the text version of this page. Right now we are in like the space version, right? Um, the text version I would say is this. Let's we could try. Oh shit, what just, oh, did I zoom in too much? Yeah, I zoomed in too much. Okay. Introduction to robot learning, getting started with LeRobot. Let's look at this. Okay, introduction, and then there's history. So this is the introduction. Yeah, I think there might be slightly different information here. That's not to say that it's like that's not to say that it's like wildly different. It's just that I think they're written in different ways. They probably give you the same information, but like I think they're just written in different ways. Okay, lately advancements in ML have sparked development of a relatively new class of methods used to tackle robotics problems, um, leveraging large amounts of data and computation rather than human expertise and modeling skills um, to develop autonomous systems. The frontier of robotics research is indeed increasingly moving away from classical model-based control paradigm, embracing the advancements made in ML, aiming to unlock monolithic perception to action control pipelines and multimodal data driven feature extraction strategies, together with reduced reliance on precise models of the world and a better positioning to benefit from the growing availability of open robotics data. While central problems in manipulation, locomotion, and whole body control demand knowledge of rigid body dynamics, contact modeling, planning under uncertainty, recent results seem to. What? How is this sentence written? While central problems in manipulation, locomotion, and whole body control demand knowledge of rigid body dynamics, contact modeling. Um, I think they meant to say and planning under uncertainty. Recent results seem to indicate learning can prove to be as effective as explicit modeling. I think I need to zoom in more. Yeah, as explicit modeling, sparking interest in the field of robot learning. This interest can be largely justified si- considering the significant challenges related to deriving accurate models of robot environment interactions. Give me a second. Let me hydrate, and then I can continue reading. Okay. Um. Right. Okay. So, uh, I'm gonna move on to the next section here. Robotics at its core. Robotics at its core, an inherently multidisciplinary field requiring a wide range of expertise in both software and hardware. Oh, maybe they meant is and oh robot. Okay, they said is at the beginning. Robotics is at its core an inherently multidisciplinary field requiring a wide range of expertise in both software and hardware. The integration of learning based techniques further broadens this spectrum of skills, raising the bar for both research and practical applications. LeRobot is an open source library designed to integrate end to end with the entire robotics stack. Okay, with a strong focus on accessible, real world robots. Just a second. Yeah, okay. Oh, here we can probably go to the end or somewhere here. Yeah, that's fine. Okay, where was I? LeRobot is an open source library designed to integrate end to end with the entire robotics stack. With a strong focus on accessible real world robots, LeRobot supports many openly available robotic platforms for manipulation, locomotion, and even whole body control. LeRobot also implements a unified low level approach to reading/writing robot configurations to extend support for other robot platforms while with relatively low effort. The library introduces LeRobot dataset, a native robotics datasets format, currently being used by the community to effectively record and share datasets. LeRobot also supports many state-of-the-art algorithms in robot learning, mainly based on reinforcement learning and behavioral cloning techniques, with efficient implementations in PyTorch and extended support to experimentation and experiments tracking. Lastly, LeRobot defines a custom optimized inference stack for robotic policies, decoupling action planning from action execution, proving effective in guaranteeing more adaptability at runtime. Okay, this tutorial serves the double purpose of providing useful references for the science behind and practical use of common robot learning techniques. To this aim, we strike to provide a rigor. Did they mean strive? To this aim, we strike to provide a rigorous, yet maybe they meant strive. Anyways, whatever. Strike to provide a rigorous yet concise overview of the core concepts behind the techniques presented, paired with practical examples of how to use such techniques concretely, with code examples in LeRobot for, for researchers and practitioners interested in the field of robot learning. This tutorial is structured as follows. Section Classical reviews Classical Robotics Foundations, introducing the imitation. Hold on, I'm cutting that off. Um, Introducing the limitations of dynamics based approaches to robotics. Section Learning RL elaborates on the limitations of dynamics based methods and introduce RL as a practical approach to solve robotics problems, considering its upsides and potential limitations. Section Learning Imitation further describes robot learning techniques that aim to solve single tasks learning, leveraging BC techniques. BC is what, behavioral cloning, I think? I think so. That word was mentioned somewhere up here. Yeah, behavioral cloning. Leveraging BC techniques to autonomously reproduce um, specific expert demonstrations. Section Learning Foundation presents recent contributions on developing generalist models for robotics applications by learning from large corpora of multitask, multi-robot data, robotics foundation models. Okay, our goal with this tutorial is to provide an intuitive explanation of the reasons various disparate ideas, disparate, whatever, various ideas from machine learning have converged and are powering the current evolution of robotics, driving the unprecedented progress we see today. We complement our presentation of the most common and recent approaches in robot learning with practical code implementations using LeRobot and start here by presenting the dataset format introduced with LeRobot. LeRobot dataset. LeRobot dataset is one of the most impactful features of LeRobot. I think I read this yesterday. In in this, LeRobot dataset provides a unified interface for handling multimodal time series data and is designed to seamlessly integrate with PyTorch and Hugging Face ecosystems. Yeah, we read this yesterday, and there's a thing about SO100, Aloha 2, and so on. Okay. Then there's the class design. Okay, we looked into this as well. Um, yeah, all of this information was there. Code example. Oh, that's interesting. So there were images the with the page version of this. So if we look here, hold on just a second. Robot learning, LeRobot dataset. There were images with this, stuff like this, for example. Um, and I think something more. Or was it just that one thing? Oh, it was just that one thing. Okay. All right. It wasn't images, it was one image. So I guess that's one difference, maybe. Now, keeping that in mind, should I be looking at the notebook or should I be looking at this, the code example thing? Because, uh, I mean, there is code here, right? You know what? Okay, we'll read this because this seems to be a lot more what's the word I'm looking for? This notebook is massive. It has all of the information, right? I feel like they've taken the information from there and cleaned it up, reformatted it to whatever extent it needs to be reformatted, and made it presentable for these kinds of pages. So like this massive notebook can then be divided into multiple or this massive page can be divided into multiple pages, and that's probably why they're also able to fit in, extra images and stuff, which has me curious. Yeah, there's images here. Do we see these images in Wait, hold up. Okay, so after the code example thing is done, we move on to classical robotics, right? Now let's take a look at if we see, because dude, like I want to see the images as well. The images help visualize things, so I kind of want to make sure that the images do exist in places, in like both of the places. Right, they do have the images here as well, so that's going to help. All right, that being said, we are probably going to follow this page instead of the massive space, but I feel like every now and then I should kind of like cross-reference both of them, um, just to see if there's like any extra information that I might be missing. But yeah, okay. This section shows you how to work with robotics datasets from Hugging Face using the LeRobot dataset class. We'll um, we'll start with simple examples and gradually add complexity so you can copy and adapt the approach that best fits your project. Okay. The key thing to understand is that any dataset on the hub that follows LeRobot's format, with tabular data, visual data, and metadata included, can be loaded with just one line of code. Awesome. When working with robotics data, you often need to look at multiple time steps at once rather than single data points. Why? Most robot learning algorithms need to see how things change over time. For example, to pick up an object, a robot might need to see what happened in what happened in the past, what happened in the last few moments to understand the current situation better. Similarly, many algorithms work better when they can plan several actions ahead rather than just deciding what to do right now. Give me a second here. Just need to hold on. Okay, where was I? Okay, LeRobot dataset makes this easy with temporal windowing. You simply declare which time offsets you want, i.e., current frame plus the two previous ones, and it automatically handles the complexity of getting those frames, even when some might be missing at the beginning or end of an episode. What is an episode here? Hold on, dude. I need to open up a conversation with Gemini. Should I have the conversation here? Hold on. Yeah. Okay. I think I can do it here. Wait. Let me. Is there anything free here that I can use? I don't want to close any of these without knowing what I'm doing. So I'll open up Gemini here. That's not Gemini. That is Gemini. Okay, so this is going to take some time to load up. In the meantime, I guess we'll continue reading. Um, Wait, is there anything we can take a look at this, right? So, delta time steps, observation, image top. Okay, okay. I'm not sure about what this list of numbers means, but let's. Oh, the list of numbers might be the time the time steps. So that's why it's saying. What does negative mean then? So is it like from this point in time backwards and then forwards as well? Okay, need to look back and ahead. Oh, yeah, okay, that's what it means. So we have 0, and then it goes -1, but then it also goes to 1 and 2. Okay, this is interesting. So is it like jumping back to -1, or, well, jumping to, not back to? Is it jumping to, like jumping from 0 to -1, and then jumping back to 0 and then to 1? Because I'm only seeing like single jumps, right? It's not like jumping back. So I'm wondering if it's a situation where it's like jumping from one to the other and then back, or if it's only ever reading like from 0 to -1, and then that's a separate thing. From 0 to 1 is a separate thing. From 0 to 2 is a separate thing. I guess we'll find out. Okay, so frame. Wait, I'm gonna need a way to display these images if I'm gonna be displaying images. Fortunately, I have my, um, oh, I could set up like a, I mean, I had that whole like data science workflow set up with Vim Slime, and I mean, I am using Python right now, right? So Vim Slime, it makes sense to activate the thing. I'll have to reconfigure it a little bit, and probably also set up an extra window in which I would be able to um, load up images. Actually, no, I don't think I'll be able to load up the images there. I'll have to. Yeah, no, I need to find a different way. I mean, I can still do it. It's just that, yeah, I need to see how to go about doing this, because I need to have the Gemini thing open. I don't have to, but like I could have the Gemini thing open. I could have. I mean, okay, I don't have to display images all the time. That's fine. Because like displaying the image, I could display it on like a different window and then just look at that window. That's mainly for me to look at. It doesn't necessarily have to appear on stream. There's that as well. So I can use one of my other systems and just have the image be displayed there. Yeah, that'll work. Okay, frame. Observation dot image dot top. Shape is so and so. Action so and so. Okay. Temporal windows explained. Observation history. Negative 0.2, negative 0.1, 0. This gives you 200 milliseconds, 100 milliseconds, and current observations. Okay. Action sequences. 0, 0.1, 0.2 provides current and next two actions 100 milliseconds apart. Automatic padding. Missing frames at episode oh yeah, hold on. I had this thing. Yeah. So let's change the model here to, let's say, Flash. I'm learning how to use LeRobot. I'm currently learning about LeRobot dataset. Hold on. Yeah. LeRobot dataset. What's an episode? Okay. Now, um, sorry, zoned out. Okay. Automatic padding. Missing frames at episode boundaries are handled automatically. The dataset always returns the requested number of frames and it applies padding where necessary. Then mask included. Know which frames are real versus padded for proper training. Okay, we got our info. We don't have our information. In the current directory? What do you mean in the current directory? Damn, this goes far back. Holy shit. I didn't realize it does this. Hold on. I'm curious about something. Okay. Okay. All right. Let's go back and read this. I need to understand what an episode is, what an episode refers to within the context of LeRobot dataset. I will search the code base for LeRobot dataset and its related usage. I couldn't find anything. However, in the context of robotics and machine learning datasets, particularly in reinforcement learning, an episode typically requires to complete, um, typically refers to a complete sequence of interactions between an agent and its environment. A complete sequence of interactions between an agent and its environment. This sequence starts this sequence starts from an initial state and ends at a terminal state or after a certain number of steps. Sorry, zoned out. Okay. This sequence starts from from an initial state and ends at a terminal at words, dude, and ends at a terminal state. Fuck me, why was that so hard to say? Or after a certain number of steps, an episode usually contains observations slash states. The agent's perception of the environment at each time step. Wait, it contains observations and states. The agent's perception of the environment at so and so. Actions, the decisions made by the agent. Hold on. So let's go back to this thing and see if that's what we're looking at. Observation history, action sequence, automatic padding, mask included. Okay, up here, what I'm seeing is something different. Um, okay, the sequence starts from words, dude. Why am I tripping up on this one sentence? This one specific sentence. This sequence starts from an initial state and ends at a terminal state or after a certain number of steps. An episode usually contains observations, actions, and rewards. So, observations, the agent's perception of the environment at each time step. Now, hold on. At each time step. Okay, all right. Then actions, the decisions made by the agent at each time step. I'm okay. I'm kind of forming an image here of what this looks like. Then rewards, the feedback received by the agent from the environment for its actions. Would you like me to search for general information about LeRobot or episode in the context of reinforcement learning? The latter. Wait, back up. The latter, please. Also, am I right to understand that an episode basically contains data? It was mentioned up here, right? Was it mentioned up here? No, it was mentioned down here. Observation gives you so and so, so and so, so and so. Current. No, okay, hold on. Um, contains data for each time step, starting from an initial times from an initial time step, all the way to however long that session lasted, and each and for each time step, we have an observation, um, a set of actions taken, and the rewards received. I think I spelled received wrong. Maybe. I'm not sure. Okay, so now there's a Google search going on. While the Google search is going on, I can read this. Yes, your understanding is correct. An episode in reinforcement learning or robotics datasets generally represents a complete self-contained run or trial for each time step within that session from initial to terminal slash end of session. It captures an observation, action, reward. Now I will proceed with a web search for more general information about episode and robotics slash reinforcement learning datasets. Wait, is it done? Oh, it's done. Okay. Based on, wait, you are absolutely right in your understanding. Okay, based on the web search, an episode in the context of robotics and reinforcement learning datasets like LeRobot dataset is precisely as you described. It's a complete self-contained sequence of interactions between an agent, like a robot, and its environment. This sequence starts from an initial time step or state and continues through all subsequent time steps until a terminal condition is met. Okay. The task is completed until a terminal condition is met. Example: the task is completed, the agent fails, or a time limit is reached. And then for each time step, it's so and so. Okay. The entire collection of these sequential state, action, reward tuples for an episode is often referred to as a trajectory. Datasets like LeRobot dataset are structured to store these trajectories as individual episodes. The collection, hold on, the entire collection, okay, often including rich data like synchronized video and so on. Wait, I'm confused. If a if if an episode is a collection of various time steps, what is a trajectory? Because it says the entire collection of these sequential tuples for an episode is often referred to as a trajectory. Okay, that's a great question, and the terms are very closely related, sometimes even used interchangeably depending on the context. Let me clarify the distinction. An episode refers to the conceptual event or a single run of an agent interacting with an environment, starting from an initial state and ending at a terminal state. Think of it as one complete game or one complete attempt. Hold on, give me a second here. I need to step away for a couple of minutes. I will be back soon. Okay, I'm back. Sorry about that. Um, Give me a second. Let me open up my stream on my phone and we should be good to go. All right. Now, oh, I also need to do something else. Open something up here. Um, think I need to. Okay. Um, all right. Okay. So, an episode refers to the conceptual event or a single run of an agent interacting with an environment, starting from an initial state and ending at a terminal state. Okay? Think of it as one complete game or one complete attempt at a task. A trajectory is the recorded sequence of data that describes that specific episode. It's the full log of everything that happened during the episode. I'm still kind of confused about this. Okay, hold on. So you can think of it in this way. An episode generates a trajectory. The episode is the process, and the trajectory is the detailed record of that process. A trajectory is typically represented as a sequence of state so and so so and so so and so tuples, or just so and so, with the next state being implicit. Um, it's represented as a sequence of so and so collected over the duration of an episode. Okay, I'm still kind of confused here. Give me a second. I'm gonna try asking Gemini Web. Maybe I might get an answer through Gemini Web. Hey, I'm learning LeRobot and am currently exploring um, LeRobot dataset or datasets. Hold on. Okay, whatever. Um, what exactly is an episode? Okay, in the context of LeRobot, an episode is a single file. Complete is a single, no, not a single file, a single complete execution of a specific task. Think of it as one full round or take of a robot trying to achieve a goal. Okay, so like one iteration, I guess. Okay, if you are teaching a robot to pick up a red block, every time you press start recording, perform the action, and then stop recording, you have created one episode. All right. Okay. So that's one iteration. Cool. Great. What is inside an episode? Same thing. We have observations, actions, timestamps. Okay. Oh, hold on. Observations, actions here doesn't mention reward. It mentions timestamps. The exact time in seconds from start to that specific episode. No, hold on. Oh, the exact time in seconds from the start of that specific episode. How it's structured in LeRobot dataset. LeRobot is designed to handle thousands of these episodes efficiently. Depending on the version you are using, the storage differs. Okay, why the episode concept matters. Task success. Usually, success or failure is determined at the end of an episode, not at the end of a single frame. Okay. Training. When training models like diffusion policy or ACT, the AI looks at chunks of frames within an episode to understand the flow of motion. And then evaluation, when testing your robot, you'll often say it succeeded in 8 out of 10 episodes. Um, Pro tip, metadata. If you look inside the meta folder of your dataset, you'll find files that define the boundaries of these episodes. Um, these, not these. This is how the dataset knows that episode 1 ends at frame 120 and episode 2 begins at frame 121. Okay, I kind of get it, but not quite. So, an episode contains um, an episode contains data for observations and actions happening at various timestamps. Exactly. You've got the core concept down. To visualize it, imagine a film strip. Each frame on that strip is a tiny slice of time. An episode is the entire reel of film that shows one complete attempt at a task. The anatomy of an episode. If you were to pause an episode at any given second, you would see a snapshot of two main things: observations, which is a state of the world at time t. This includes the camera feed, pixels, and the robot's current joint angles. Uh, Proprioception. That's a new word. Hold on. Let me look that up. Proprioception. Proprioception is your body's unconscious sense of its own position, movement, and force, relying on receptors in your muscles, joints, and tendons to send constant feedback to your brain, allowing for coordinated movement, balance, and awareness without needing to look at your limbs. Give me a second. Okay. Right. So first we have observation, and then the next thing in the snapshot would be actions, the command given to the motors at time t to get the next state. How it looks in the data. In LeRobot, you have the timestamp, the image, which is the observation, observation.images.top. Okay. Then we have observation state, which is the joint state. Oh, that's what the state is. Okay. It's the state of the robot at that time. Okay. So somehow I didn't connect it. And then we have action, which is the motor commands. All right. Why this structure is vital for AI. When you train a robot, the model is essentially learning a mathematical function. Um, Action equals F observation. The reason we group these into episodes is that the robot needs to understand context. To pick up a block, the robot needs to know not just where its hand is now, but often where it was few frames ago to maintain smooth motion. By keeping frames grouped in episodes, the LeRobot loaders can easily grab a window of frames, example the last 10 frames, to give the AI short-term memory. All right, that's good enough for me. That is good enough for me. Right. So, um, moving on. Know which frames are real versus padded for proper training. Automatic padding. Missing frames at episode boundaries are handled automatically. The dataset always returns the requested number of frames and it applies padding where necessary. Okay, so it fills in data. Great. Awesome. Conveniently, by using LeRobot dataset with a PyTorch data loader, one can automatically collate the individual sample dictionaries from the dataset into a single dictionary of batch tensors for downstream training or inference. LeRobot dataset also natively supports streaming mode for datasets. Users can stream data of a large dataset hosted on the Hugging Face hub with one line change in their implementation. Streaming datasets supports high performance batch processing. Um, okay, and high levels of frame high levels of frames randomization, key features for practical BC algorithms, which otherwise may be slow or operating on high non-IID data. Okay, no idea what that means. I guess we'll learn that later on. Actually, no, I want to learn it now. Give me a second. I'm gonna look it up. Non-IID data. Sorry, zoned out. Okay, non-IID data, non-independent and identically distributed data means data points aren't dependent. No, data points aren't independent or don't come from the same distribution. N- Hold on. Um, Non-IID data means data points aren't independent or don't come from the same distribution. Okay, so data points being independent and data points being part of the same distribution are two different things. So non-independent and identically distributed. Okay, right. It means they don't come from right. Okay, data points aren't independently words. Non-IID data means data points aren't independent or don't come from the same distribution, violating core machine learning assumptions common in real world scenarios like user preferences changing over time or different clients in federated learning having varied data. Example, only one user. Okay, all right, whatever. Leading to challenges like slower model convergence, and poor generalization, especially in distributed systems where data naturally varies by location, user, or time. Okay, all right. That's good enough for me. I'll need I'll need some time to understand like exactly what this entails, but for now that's enough. Um, this feature is designed to improve. I'm continuing reading the course thing now. This feature is designed to improve on accessibility so that large datasets can be processed by users without requiring large amounts of memory and storage. Here are different ways to set up temporal windows um, depending on your use case. Skim the options and pick one to start. Switching later is just a change to the dictionary. Really? Okay, hold up. All right. Okay. Basic behavioral cloning. Learn current action from current observation. Sorry, zoned out. Okay, let's give this a try. Let's see. I don't know how long this is going to take to download. We're just gonna try it out. LeRobot dataset. I think I need to import that from LeRobot. Import Lero. That's not working. Um, from LeRobot. Import LeRobot dataset. Is this gonna work? Yeah, I don't know if this. What are we supposed to be using up here? Let's see if there's any code. There's nothing here. Um, where am I pulling LeRobot dataset from? From LeRobot.datasets, LeRobot dataset import. Okay, that's where I'm pulling it from. From uh, LeRobot.datasets.LeRobot dataset import. Let's see if that completes. Yes, it does. Okay, dataset equals. Okay, streaming large datasets. What is this? Behavioral cloning. Okay, let's create the delta timestamps. That's going to be a dictionary, observation.images.up. And this contains a list of just one item. And action is also a list of one item. A robot dataset, LeRobot slash SVLA underscore SO 101 underscore pick place. And then delta timestamps equals delta timestamps. Now we're going to run the, what's the issue? Argument of type dict cannot be assigned to parameter delta timestamps of type what? Dict list float. What did I give? Wait, I'm missing something here. Um, hold on. First things first. Let's do that. Okay. Uh, observation dot images so and so so and so. Okay. back up. Let's read this again. Argument of type dict str list float. Okay. Cannot be assigned to parameter so and so timestamps of type dict list float unknown. Okay. That is odd. I wonder if this is just I wonder if this will still be accepted. Maybe it might still be accepted. Um, let's do it here. Let's go back and go into, wait, go back here and then learning, LeRobot and this source env bin activate Python 3.14 pi. Okay, let's see how big this data set is to download. Because I'd imagine it contains like images as well. Wait, is it throwing an error or not? Is this a warning or is it an error? I think it's just a warning, right? Yeah, it says syntax warning. Okay. Let's see what's going on. Okay, download, download, download. I'm trying to look for sizes. Download complete. That was 122 KB. You are sending unauthenticated requests to the hub. Please set a HF token to enable higher rate warning, to enable higher rate limits and faster down. That's fair. Okay. I didn't know that it works in that way. So like if you give them a token, then you'll get a higher rate limit. Download complete 86 MB. All right. Run it again. I hope there's some sort of like caching mechanism. Right, so our issue here is what exactly? Dude, this is a lot to like trace back. Can I copy this into my, yeah, I think I'll do that. Let's copy this entire thing and feed it into Gemini. Um, let's do that and do that. Hey, I'm trying to use LeRobot dataset to download a dataset, but I'm getting an error of, actually, am I getting an error? Yeah, it's red. Type error. Uh, Pickler.batch set items takes 2 positional arguments, but 3 were given. Okay. Um, but I'm getting an error of some sort. Um, can I post the error here and you take a look? Okay. All right, it looks like you've hit a classic bleeding edge compatibility issue. The error so and so is happening because you are using Python 3.14. The problem, Python 3.14, which is currently in pre-release slash experimental stages, introduced changes to the internal pickle module. The libraries dill and Hugging Face datasets, which LeRobot relies on, haven't been fully updated to support the internal API changes of Python 3.14 yet. Specifically, the way the pickler class handles dictionary items has changed, causing the type error. The fix is to downgrade to Python 3.10, 3.11, or 3.12. For robotics and AI libraries like LeRobot, um, it is highly recommended to stay on a stable, widely supported Python version. Most of the ecosystem is currently optimized for 3.10 or 3.11. You know what? That's fine. I feel like 3.10 or 3.11 is like still way too low. Um, so, okay, we can try something here. Okay. Oh shit. I'm gonna need to install PyTorch again. I mean, it's downloaded and cached, right? No, it's been downloaded for Python 3.1. Hold on. Let me look up LeRobot Python version. They've probably mentioned it in the GitHub repo. Um, pip install LeRobot. Okay. Installation documentation. All right. LeRobot dataset. Okay, create a virtual environment with Python 3.10. Okay, all right. So I need Python 3.10 for this. Install from PyPy. Okay, okay, okay. All right, now let me go take a look at, because I'm going to need to reinstall PyTorch, right? PyTorch 3.10. Py, PyTorch PyTorch is supported for 3.10, at least from what I remember, because it's between 3.10 and 3.14. Okay, Python pip CPU. Okay, okay, okay. All right. Give me a second here. Where does it mention the Python? Oh, yeah. Python 3.10 to 3.14 is generally installed by default. I probably have 3.10. I do not. Okay, so then I guess I'm installed. Wait, now let me try it. I do not. Okay. UV, um, I think it was Python install 3.10. All right, we have Python 3.10 hopefully installed. There it is. Great. Awesome. So now we create, actually, I need to destroy this environment first. I don't need to remove that. I just need to remove this. So that's gone. Now we do uv pip, no, uv venv p 3.10 env. Now that we have that environment, let's activate the environment. And now we need to install PyTorch. So let's install PyTorch. UV pip 3 install. Okay, pip install. Yeah, I think it's going to be downloading. It's going to be downloading a bunch of things now. And then finally, we'll be installing LeRobot, and we'll then reopen this. We'll then reopen this project. Oh, backup. I forgot to close this. That's, oops. Can I still do deactivate? Because yeah, okay. Okay, okay. This is, um, right. I mean, the download is going pretty quick. Okay, we are done. Then uv pip install LeRobot. While this is doing its thing, oh, okay. It has to download a bunch of packages, which it is doing now. Good. It's all going relatively quick. However, stop. No, no, no. Stop. Um, how do I stop it? Stop. Why is it doing that? Why is it downloading the CUDA stuff? It's not supposed to be downloading the CUDA stuff. Okay, so I'm gonna need to look into this and figure out why exactly it's downloading the the CUDA stuff. But yeah, okay. Um, for the time being, I think that's gonna be it. We also seem to be losing frames, which is interesting. I don't know how long that's been going on. We did lose a couple of frames, but we seem to be good so far. Now, give me a second here. Studying the blade, quantum math. That's interesting. There's someone studying quantum math right now. Okay, okay. Mastering data tools until I get the remote data job. I like that. This is a data science person. Uh, let's see who. Oh, do you know what? Actually, okay, there's a couple here. Yeah. Wait. What is? Yeah, you know what? We are gonna go back to Louise McJagger, who we rated yesterday. Oh, don't. Okay. Yeah, we're gonna go back to Louise McJagger. Louise is chill. Louise is cool. Um, I'm gonna start up the raid. Okay, so we made a bit of progress here. I need to fix whatever issue is going on here because we managed to solve the issue with another version of Python, but then with this version of Python, we are having this issue. So I'm going to need to look into this again because I don't want to download and install the whole CUDA thing when I'm not doing CUDA at all. Um, yeah, yeah. But I'm happy with the progress that I've made. I'm gonna see because I do kind of want to learn this on stream, not off stream. I do want to also practice it off stream, but then I want to learn a lot of it on stream. So then, you guys also get to learn. And I guess off stream, I'll continue my Rust studies and finish learning the basics so that I can get started with those plenty of other project ideas that I have in mind. And yeah, dude. Yeah, I guess that's gonna be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.